All right, how's it going? Everybody survived the snow. So I want to go over the study guide I posted for the midterm, talk a little about the midterm, and then mostly we're going to talk about trees some more. And I want to talk about recursion in general, and we'll look at some details of working with trees. Any questions before we jump into all of that? I had some people ask me about PA3, about using arrays versus lists. You're required to use lists to implement PA3, but I don't think PA3 should take you a full 2 weeks. If you've done PA2, you've already got the basic structure of linked list manipulation. PA3 shouldn't be really super time intensive, right? So it's not a bad exercise to re-implement PA3, make a new version of it, where you implement your stacks and your queues using arrays instead of linked lists. And it should be no change to your main program, or maybe a minimal change to your main program, but your function calls should be the same. You have to change the function prototypes, but it can be a useful exercise, one, for learning more about stacks and queues in general, two, for nailing down how you would implement them with arrays, which you may see, somewhere in a future course. And it also helps you think more about abstract data types, right? If you find that you have to change large pieces of your main program when you do this, then there may be something you're doing in your main program that should be done below the user level, right? And so it can sort of help you understand those concepts. So that's something if you're done with PA3 and you're totally bored and you're like, I wish I had some code to write, right? That can be a good exercise to work on. All right, so I just reposted this because I didn't include hashes on here before, so I just put hashes on. No real big surprises here, right? This is basically what we've been doing, things that you should be pretty familiar with for the midterm. So everything we're doing deals with structures, right? So these composite data types that we define on our own. So struct, structure name, curly bracket, list of field declarations, closing curly bracket, semicolon. That gives us a composite variable. When you want to access parts of a structure, so if we say, and I'll just pick on a node because we're using nodes. If I say struct node n, I can say something like n.data equals 5. I could say n.next equals Malloc, or whatever, right? But I don't want to do something like n arrow data. That's a syntax error. Why? Because n is not a pointer. N is a struct node. So I access fields by using this period. What we normally do is we have a struct node pointer. Let me call it PTR. And so here I could say PTR, thing that it points to. This is a struct node. This is just like n now. So I could say take this thing dot data and set that equal to 5. But our preferred way to do this would be to say pointer arrow data. And this is exactly the same. So pointer arrow data, think of it as the same as pointer dot data, except this is actually a pointer to a struct node. So the arrow says first take the thing it points to and then grab the field name data. Or pointer arrow next, or things like that. And in this case, if we tried to say something like pointer dot data, that's a syntax error. So you've been doing that for a few weeks, right? So declaring a structure, making a pointer to a structure, allocating memory for a structure is Malloc. right? So you call Malloc, you tell it how many bytes you want, and it returns the address of a block of memory that's big enough to hold whatever you asked it to hold. And so typically if we have a pointer to a struct node star, we would say something like pointer equals Malloc and tell it how many bytes we want. Okay, how many bytes do we want? We don't really want to put in magic numbers because those change over time. So the preferred way is to say size of parentheses, and then we want to list a type of variable. Avoid putting in the name of an actual variable. I wouldn't say PTR, I would say size of struct node, right? If I wanted enough space for a struct node. I wouldn't say n, I'd say size of struct node. So accessing fields, arrays of structures are just like arrays of anything else. We can say struct node array bracket 10, that's an array of 10 nodes. We don't usually do arrays of structures at this point. We're really just dealing with here's a node, there's another node, and we hook them up with pointers. All right, linked lists. You'll see linked lists on the midterm for sure. I can promise you that. So sentinel nodes, what is a sentinel? Why do we have a sentinel? What does it do for us? It ensures that if there's nothing in the list, if we haven't stored any data in the list, we still have one node. Okay, so an empty list doesn't disappear and become null. There's always one node, and that's not actually part of the list that we're thinking of. That's just a thing that points to the first node of the actual list.
It's essentially a placeholder?
It's kind of a placeholder, but it never actually becomes a part of the list. So I usually think of it as a handle, right? It's a thing that you can use to drag around the list, right? It's like a handle on a coffee cup. Even if the coffee cup is empty, you still have a handle on it, right? And then if you put some stuff in the coffee cup, there's coffee in it. If the cup is empty, the handle doesn't disappear, right? It's a way to sort of take hold of the list and pass it to a function or get it back from a function and so on. So it's kind of like a placeholder. Let's see, so searching a list, traversing a list, inserting, deleting, you've been doing all of this. You're doing this with stacks and queues as well. PA1, PA2 in particular, so you should know those algorithms. I will not ask you to write an insert function. I will not ask you to write a delete function. Okay, you've done this in programming assignments. If you bring your code with you, you just have to copy it down onto your exam. That doesn't do any good. So, so I won't be asking you to write exactly functions that you've already done, but pieces of functions or slight variations on functions you've done or operations on lists. Those are all likely candidates. Doubly linked list, you just have pointers going forward and backward. So add a back pointer to each node and it points to the previous node. Circular lists I forgot to put on there, but the last node, instead of pointing to null, points back to the beginning. So small variations on there. Order of complexity. So I don't plan to go crazy on this, but I'd like you to know the basic ideas of order of complexity because that motivates a lot of what we're doing. So what are some of the things we talked about? If you have just a plain old array of stuff and it's not in any particular order and you want to add something to that array, all you got to do is add it to the next location, right? So that's an order one operation. Doesn't matter how big your array is. If you got 10 million things, the next entry just goes at index 10,000,001. But searching an array like that is really expensive because if you're searching for something and there's 10 million things and it's not sorted, you got to search every single location, see if this is what you're looking for. So search becomes what we call order n. It's linear with the size of the array. If we sort the array, we can play high-low, keep cutting the array in half. Our search time goes down to log n. But then insert becomes expensive because to put something in the middle, we've got to move everything down to make space for it. So a sorted array is faster to search but slower to insert. So we came up with linked lists, which are a way that we can insert in the middle of a collection of things without having to move everything in memory, because we can just create a new node, point to that from the middle, and then point to the remainder of the list. So inserting into a linked list is efficient, but searching is back to problematic because we can't jump into the middle of the list and subdivide. So what we're talking about going forward is trees, which address that search issue. Trees aren't going to be on the midterm. So basic order of complexity. Lists versus arrays, yeah, so complexity of amount of work you have to do to insert into a list versus an array, search a list versus an array. All right, star and ampersand and arrow. So you know these concepts, but if they're going to confuse you in the heat of battle, put some notes down on your note sheet. So here's the way I think of it. If I say variable, I'm asking for the value of that variable. If somewhere I said var equals 5, and I say print out var, it's going to print a 5. Okay, that's just the value of the variable. If I say star var, this is whatever is stored at memory var. In other words, var is the address of something. And so I want the value of that something. So if var is equal to 5 and I say print out star var, it's not going to print a 5. It's going to say 5 is the address of something in memory. It's going to go to location 5 in memory, see what's stored there, that's what it's going to print. Okay, it's an indirect reference. So var is a pointer to something in memory. Star var says, show me what it's pointing to. Ampersand var is the address where var is stored. So I could say var equals 5. If I print out var, it's going to print 5. If I print out star var, it's going to go location 5 in memory, and whatever's stored there, that's what it's going to print. If I say ampersand var, it's going to say, where am I storing this variable in memory? Doesn't matter what the value of it is, but somewhere down here at location, 20,160, that might be where it's storing var. So ampersand var would give me 20,160. All right, so address of a variable, thing pointed to by a variable, and they're kind of complementary. And the arrow means take the thing pointed to by the variable and give me the field. So you've been using these since 121, but like I say, if they still might trip you up during a test, right? Put something down in your notes to remind you. Put some examples or whatever will jog your memory. Pass by value versus reference. So this is more of a concept than anything else, but the basic idea is C always passes by value. So if I say function I can do anything I want inside my function. When I come back, I is going to have the same value it did before I called the function. My function is never going to change the value of this variable. Because when I call function of I, the system says, what's the value of I? I is 5. Okay, it calls function and it passes a 5 to it. Even if you do a pointer, the thing you pass will never change. Now if I say function ampersand I might change, but the address of I is not going to change. Right? The actual thing that you pass is passed by value. And some languages pass by reference. Some languages, if I say function I, it will actually pass the address of I. And then in my function, if I say I equals 10, it'll actually come back up, and when I return from my function, I'll magically be 10. Okay, C doesn't do that. So the way we deal with that, if we want our function to change a value, is we pass the address of a variable. And then it can pass the variable it can change the variable whose address we passed. Malloc free and Valgrind. So Malloc allocates memory, free demallocs memory, right? And you can only call free with something that you got from Malloc. You can't free an arbitrary location. But if Malloc gave you blah, you can say free blah, and it'll release it. If you say free blah plus 2 or something that didn't come from Malloc, you get those warnings when you run Valgrind. And Valgrind is your tool to help you check your housekeeping, make sure that you freed everything that you malloced, and you're only freeing things that you malloced, and so on and so forth. All right, GDB. What do you want to know about GDB? If you want to compile, throw in the G switch. Right? If you're not using GDB and you say GCC purple rectangle, if you want to compile with GDB, you say GCC-G purple rectangle. -O, -C, A.C, B.C, main.O, whatever else you're going to put in there, just throw in a -G switch right in the beginning. That links you up for GDB. And then GDB, executable. Again, whatever you would type to run your program, just say GDB, whatever you would type to run your program. And that starts your program in GDB. And then what do we have? We have start, which begins debugging. We can say break. And we can either say break line number, or we can say break function name. Those are our two main ways. So if you want to stop in your insert function, you can say break insert. And they'll put a breakpoint at the beginning of insert. And then we can say continue, which says run until you hit a breakpoint. We can say next, which says do a single instruction. But if that instruction is a call, it will do everything in that function call and return before we get back. We can say step, which says jump into this function that you're about to start executing and then stop. Come back to me right away. So step into versus step over with next. We can say print to print the value of a variable. We can say X if we want to examine raw memory. We can say watch to set a watch point on a variable. You did that in the GDB quiz, which says if you're running, or if you've continued, stop running when this variable changes value. Is there anything else? I think that's the bulk of it. That's almost everything that you need to do in GDB.
If you're using GDB on a program that's having multiple files, and how does the line number work in relationship to that?
There's other things you can do where you can say file name : line number, but it's easiest when you're setting breakpoints to use function names. That's usually the cleanest. But yeah, there are ways to do that. Anybody tried GDB on Rogue yet? Anybody downloaded the source code?
A quick question about GDB. Is there a way or a command to display the disassembled, or sorry, no, the code, or like?
Yeah. So your X command for examining memory takes switches. So if you say X/I, it'll show the instructions in assembly language.
I mean, like when you do the G flag, it compiles the.
No, it'll disassemble on the fly. It'll look at the whatever location you're pointing to, and it'll reverse the assembly process and give you assembly language code. No comments, no variable names, but it'll show you the instructions. Yeah.
So the next is step into, and the step is step.
Next is step over,
Oh.
and step is step into.
And then continue goes
Until a breakpoint or a watch point or your program exits.
okay.
if you're going into assembly, the other good command is layout, ASM. If you do that, it'll open up a pair of windows using curses, and you'll actually see a chunk of code with the assembly language disassembled, and you can step through with step or next, and it'll move a little cursor and show you what instructions being executed, and I think it'll show you your register contents and stuff like that. So that's really handy if you're trying to dig into code.
What
This-
about Valgrind?
What about Valgrind? Valgrind, run it on your program, and it'll track your mallocs and frees. And when your program exits, it'll give you a report and tell you how you did. Do you have any memory leaks?
Layout ASM is not on the midterm, is it?
No, no. The only thing I need you to know on GDB is really this. But it's a tiny little piece of what GDB can do. Right? So if you want to be a power GDB user, there's tons of stuff out there that it'll do. There's initialization files, there's a layout command, there's disassemble commands, things like that. You can pull in symbol files from outside and augment your session. All right, make files. So purpose of a make file is to control what gets compiled and linked when you need to rebuild your executable. So it's a way to sort of systematize constructing an executable program, so that all you have to do is say make. And the make file contains a collection of instructions that say what depends on what, and it'll look at the modification dates on different files and decide what needs to be recompiled, what needs to be linked, and it'll give you an executable at the end. And if you haven't made peace with make files, grab a make file from lecture notes or somewhere and just throw it in a spare directory, put some files and mess around with it. Right? It's not complex once you know how the pieces work. The idea of a recipe and dependencies, once you nail those two, it's really straightforward to put them together. You just have to mess with it to get it to work. And if it's not working for you, right, perfect question to post on a discussion area. Hey, here's my make file, this is what I wanted to do, when I run it, this is what it does, I'm stuck. Any ideas, right? And we can talk about it. You had your hand up?
Oh, I did.
Yeah.
So I had a question about why is it that we don't include header or like .h files inside of the make files?
You would include them as a dependency. So let's say we've got a main program, main.c, and you include list.h, which prototypes my functions, for example. So in my make file, thanks. So we've got main.c, it includes list.h. So in my make file, how do I build main.o? It's going to depend on main.c. So if main.c changes, I need to rebuild my object. It's definitely going to depend on list.h. If list.h changes, I'm going to have to rebuild my object because my C code has changed. My command for this would be gcc-c main.c. I don't have to list list.h here, right? I don't need to tell gcc anything about list.h because main.c has an include statement. Okay, so that will automatically pull in list.h. And if I put list.h down here, then I get this weird extra file in my directory, which is like a precompiled version of list.h. My executable depends on main.o, but it doesn't depend on list.h directly. If I have main.o, I don't need list.h because main.o has already been compiled from main.c, which already included list.h. So to build my main, I'd say something like gcc-o main.o. Does that make sense? Okay.
So I have two questions.
Yeah.
With .o, is there any benefit for us using .o right now?
Using .o
Yeah.
like this,
Yeah, because we could do that, or we could just have a main.
or you just have a main.
So what's the benefit of us using .o right now?
If you have only one file, which is main.c, there's probably no benefit to doing this. But if you have two files, main.c and list.c, right, this is slightly faster. Practically speaking, makes no difference. But, you know, if it grows to where you have 1,000 files, right, significantly faster to just have a bunch of .o's, because then if you just change one file, you only recompile that one file. So it's mostly just practice for like the larger projects. Was that your second question? Or your first? Okay.
So I have like a lot of functions, and in the functions I just use include.h.
Mm-hmm.
So in my make file, I have just the main and then the gcc.h in there once. Is that also acceptable?
So when you say you have functions in your .h, do you have just the prototypes, or do you also have the code?
I have, in my .h, I have the structures, the definitions, and the include, standard IO, and all those things.
Okay, so where are the actual functions? Like add and insert and delete, are those?
They're separate. They're there, and then I have in the function include.h, and then in my make file, I have, insert.o.
Okay, so you have an insert.c, it turns into an insert.o?
Yeah.
Okay, good, good. So ask your question again then?
And so I have my list.h just once in my main executable.
If main's the only thing that includes it, then yeah, it would only be in this line. But if your insert function needed to use something that was defined in list.h, then you'd include list.h in your insert.c, and then your insert.o would depend on insert.c and list.h. But if this doesn't include list.h, you don't need to list that as a dependency. Yeah?
If we were going to include something like the math library or something, would we add that to the GCC part of that?
You could. You typically wouldn't, because we kind of assume that's not going to change, just like stdio.
Right.
But if it was, something like that that had been produced by someone, at your company for some specific thing on your system, and it might change periodically, you might list it as a dependency. But typically, no. Typically, this is just going to be pieces of your project.
Well, how come we have to link the math library when we call GCC normally? It's not.
Because it's just not included in the list of things to link. There's so many libraries out there, and if you specify them all as potentially interesting, it's got to go through and it's got to, deal with all of these files. So fgets and scanf and these kinds of things, we assume that most programs will need these, and so those are included in the standard include path. But math and DBM and all these other things aren't included by default. So it's just decisions that were made. And you can change those. You could change the default, or you could just make your own GCC command that automatically does a -lm at the end or something. But if you have a make file, you don't have to worry about it. You put it in one spot in there, put a -lm on the end, and you just say make. All right, abstract data types. General concept here, anytime that we develop a data structure, there's sort of two pieces to it. There's the piece the user is going to see when they're using the data structure, the way that they interact with it. That's the abstract view of the data structure. There's how we actually implement it, the stuff that's under the hood. That's the gory details, right? That's the implementation details. So we're making a linked list. Do we have an array? Do we have struct node pointers that we call malloc? Do we have a magic my_null that's equal to -1? None of that should concern the user. As an abstract data type, a list is a set of functions that let you initialize, insert, delete, search, print. That's it. So just this idea of a separation, right? A stack has some way to say push something, pop something. Is a stack empty? Is a stack full? All right. Is that done with a variable called top of stack? Is it done with a linked list? Is it done with someone in their dorm room with a whiteboard and a phone? Those are details the user doesn't care about. They just want to say push, and if they say pop, they get the last thing they pushed. So separation of layers. So stacks and queues and hashes, I will not ask you to do any coding around those. Okay, I just want you to know concepts. So concepts of a stack, there's a push and a pop. Right? Pop always gives you the last thing that you pushed. Think, if you like, plate of dishes, pile of dishes at the buffet. The last dish that you put on top, that's the first one you take off. Okay. If you can't put any more things on the stack and you try to, that's an overflow. If you try to pop something from the stack and there's nothing there to pop, that's an underflow. Queues, we put things in on one side and we take them out from the other side. So think checkout line at a store. People go in through one side and they come out the other. The first person who gets in line, they're the first one who's going to come out. 100 people come in behind them, doesn't matter. The first person who's going to be serviced and come out of the queue is the first one who showed up. The 100th person in line will be the 100th person taken care of. So queues, we talk about insert and remove. Insert at the tail, remove from the head. Okay, that's our standardized terminology here. You'll find places online that reverse those. But for us, it's always insert at the tail, remove from the head. And then a queue can be full if there's no space left to put anything in. It can be empty if there's nothing in the queue. Hashes, basic concepts. So why do we deal with hashes? Because theoretically they give us order 1 performance for insert and search and delete. And they do this with a hash function. The whole purpose of the hash function is to take a key and tell us where that key belongs in an array. So without a hash, you have an array with a bunch of keys stored in it. How do you figure out if the key's in there? You check every single entry. Or if the keys are sorted, you do a high-low binary search. With a hash, someone gives us a key. We want to know, is this key in the array? We run it through the hash function. The hash function says this key should go at location 17. We go straight to location 17 and we look there for our key. And if we find it, good. And if that location is empty, then the key's probably not in the hash. So that gets complicated when we have collisions, and I won't get you real deep on collisions, but basically 2 keys might try to go into the same location in your array, and you have to have a way to deal with that. That's called a collision. And we deal with that one way is by probing. So we can get this hash function to give us different answers. The first time we hash our key, it might give us 17. We say, that's no good, 17's in use. Give me another number. So we rehash with a different probe value, and it says, okay, try location 205. And then if 205 is free, we'll store it in 205. So concepts there, again, no coding. Things you should be prepared to do, same business as usual. So writing some code, so there's going to be 3 coding questions, and then I think 11 short answer, fill in the blank, multiple choice kind of questions. So writing code to manipulate structures, work with pointers, dereference pointers, things like that. I might give you some code and ask you some questions about it. Could give you some code and ask you to make changes to it. So a combination of analyzing and writing. I'm not going to ask you to discuss performance of algorithms, like write an essay or something, but just basic concepts, right? And then understanding and being able to do operations on lists, stacks, and queues. Right, lists including coding. And then short answers, multiple choices related to GDB, valgrind, make files, those kinds of things. All right, good enough? So this is Friday, so don't miss it. Hopefully we don't get like bad snow on Friday. If we get bad snow on Friday, right, and it's not safe to drive, don't drive, okay?
So we got 100 if we don't.
Say what?
So we all got 100 right? If we
No, no, you got a special midterm to do later. But no, seriously, like you know, for this course, or I would say for any course, if, you know, particularly you live off where it tends to snow more, or the roads aren't as good, and something, because they're predicting snow towards the end of the week. So if something happens, right, don't take risks. We'll figure something out. All right, any questions? All right, let's talk about trees some more. So, as an abstract data type, what kinds of things do we want to do with trees? We might have some sort of initialize routine, but in general, since we're not going to have sentinel nodes, initializing a tree is really just going to be setting a tree equal to null. So we don't really need a separate initialize routine. But we definitely want to be able to insert data into trees. We want to be able to search a tree for data. We want to be able to say remove a piece of data from a tree. We want some way to print the contents of a tree, and a more useful function than print would be some kind of traversal. So something like when we talked about traversing a hash, we talked about iterators. So maybe something that says, bless you, says give me the first node of the tree, give me the next node of the tree, give me the next node of the tree, keep doing that until the tree is empty. So we can retrieve the data from the tree one piece at a time, and we can choose to print it or do something else with it, right? But for us, we're really just going to think about, let's just print the data in the tree. And we might want to print it in different orders, in order, pre-order, post-order. And in general, a print function is not terribly useful, because a lot of times you want to look at the data without printing it on the screen, right? But for us, we'll mostly just think about a print function. We probably want something that lets us release the tree, free all of the memory, send it back into the pool of available memory, so that when you're done with PA4, you don't have any memory leaks left over. And then we may want to be able to do some analysis on a tree. For example, determining the height of a tree. And remember, the height of a tree is the depth of the deepest node. And it's useful to be able to know what the height of a tree is, because height corresponds roughly to how much work we have to do to, say, search this tree. Remember, when we search for something in a tree, we start at the root, we move left or right at each point until we get to our node or we run out of stuff to search. Well, the number of times you have to do that basically corresponds to how deep the node is that you're moving towards. And the height of the tree is the depth of the deepest node. So the tree height basically tells us how much work we have to do. And it can be useful to be able to find the height with a function call. So let's look at a tree. And this is going to be another random drawing. So don't worry too much about copying it exactly. You can just watch my beautiful drawing techniques. All right, here's a tree T. We want to know the height of this tree. That means we have to find the depth of the deepest node. Now you and I, we have these wonderful brains and a big optic nerve, and we can look at this and we can say, okay, there's the deepest node. So starting at the root, 1, 2, 3, 4, 5, 6, 7, 8, height's equal to 8. It's easy, right? So how do we tell a computer how to do that? Not so easy. The computer really has no choice but to find the depth of every single node and keep track of what the deepest depth was. And then when it's done this for all nodes, tell us what the maximum was. And how do we find every single node in a tree? Well, that's a little bit complicated too. because we can start from the root, but right away we've got a decision to make. Should we go this way or that way? And if we decide to go this way, we've eventually got to come back and go that way, because the deepest node could be over here on the right. Same thing here. When we get to this point, we could go left, but eventually we got to come back and go right. And so you've got to have some way to keep track of all of this stuff. So we can use a stack, or we could try to use some recursion. But you got to ultimately run through every possible path. And as you're doing that, you got to be adding or subtracting or saving heights, saving depths at each point, so that when you get down here, you know, okay, well, this was a height of depth of 7, this is a depth of 8. And then you got to have some evil global variable where you can store that maximum, so that when you finish this whole process, this global variable is set to whatever the deepest amount was. So what we're going to do right now is something that you'll see again and again the rest of this course, which is we're going to step way back from what I just said, and we're going to try to find a lazier way to do something. And we're going to have to rethink what we're trying to do from the beginning. We're trying to find the depth of the deepest node. But I'm not going to do that. I'm going to do something different. I'm going to make an observation as follows. Here's my original tree T. This is comprised of a root and 2 subtrees. There's a tree over here, which I can think of as T dot left, and a tree over here, which I can think of as T dot right. If this was C code, I'd use arrows, but I'm just thinking abstractly here. So there's a root node, there's a left subtree, there's a right subtree. What's the height of this right subtree? Well, there's the deepest node, 1, 2, 3, 4. What's the height of this left subtree? Yeah, deepest node, 1, 2, 3, 4, 5, 6, 7. What's the height of the entire tree relative to those 2 heights?
0.
I've got a 7 and a 4. How do I get an 8 out of those?
Height of the largest plus 1.
The height of the largest plus 1. Because whichever one of these is taller, has a bigger height, that contains the deepest node. And if I include the root, the depth of that node goes up by 1. So the height of the entire tree is 1 plus, and let's assume we have a maximum function that takes 2 things and gives you the maximum. It's the maximum of the height of T left or the height of T right. That formula gives me the height of the tree T. And so if I say return that, there's a 1-line height function. And it's a cheat. We're not doing anything. We're not looking at nodes. We're not calculating depth. We're not remembering the maximum depth of a node. We're just saying, give me the height of the 2 subtrees, whichever one's bigger, add 1, there's the height of the tree. And this really works. We need one more line of code in here, though. Because if I ask for the height of a tree, it's going to ask for the height of some smaller trees. And this call to height is going to ask for the height of a smaller tree. And it's going to keep asking for the height of smaller and smaller and smaller trees. Eventually my tree is going to be null. And if I ask for the height of a null tree, it's going to ask for the left subtree of null, and null doesn't have a left subtree, so I'll segfault. So I got to have a special check here if t equals null. So what's the height of a null tree? Do you remember? Negative 1. It's not logical, but... And there's a perfectly good height function. Say it returns an int. So if the tree is null, return -1, otherwise return 1 plus the maximum of those two heights. Recursive height. Right, so what's the collaboratorium example, right? Someone hands you this tree and says, tell me the height, and you cut out this piece, hand it to a friend, say, tell me the height of this, please. Cut out this piece, hand it to another friend, tell me the height of this, please. 7 and 4, you take the largest one, 8, tell the person who asked you the height's 8. You didn't have to do much work.
Why do we return -1?
That's the definition of the height of a null tree.
Okay.
But I said, when I said that the other day, I said we do that because it makes things work. This is one of the things that it makes work. Because suppose we asked for the height of a tree consisting of just a root, right? And we know this should have a height 0 because the depth of this node is 0. Well, our recursive function will say our tree is not null. So let's take the height of the left and the right subtrees. Well, the left subtree and the right subtree are both null. So the height function will return -1. Maximum of -1 minus 1 is -1. Add 1, that's a 0. So our height function will return 0, which is exactly what we want. So the real reason why it's -1 is because that's 1 less than 0. But that's not totally satisfying. All right, so we're going to work almost exclusively with recursive algorithms from here on out. And they're going to make our life a whole lot easier. So let me give you one more example. Let's think about a linked list with no sentinel. We're going to forget about sentinel nodes after Friday until the final exam, because we're not going to use sentinels in trees. Okay, but let's think about a linked list with no sentinel. So our list looks like this, or it's just null if our list is empty. So let's write a myPrint function that prints out the nodes in the linked list. So someone hands you this list and says, hey, can you give me a printout of all of this, write it down on this piece of paper? Right? We could go through and we could follow the pointers and we could go through a while loop until we get to null. It's a lot of work, right? So what's the lazy approach? No sentinel. So the lazy approach, we'll print out the first node's data, right? Well, we can't do this if there's nothing in the list, so we have to check to say if list is null, we'll just return, because there's nothing to print. But if there's at least one node here, we'll print out its data, and then we'll say, I'm tired, I'm done. Hey, can you print out the rest of this list for me? Get your friend to print out the remainder of the list, and you're finished. So there's a 3-line print function for a list. And there's no looping. There's no keeping track of temporary variables. There's no previous current business. Right? If the list is empty, do nothing. Otherwise, print out the first node's data. And then call this handy myPrint function, hand it the rest of the list, and let that do all the other work. And that's a perfectly good print function. It's recursive. All right, so we'll dabble with this a little more tomorrow. We'll look at, think about how you would do this to search a list recursively. And see if you can come up with that. It's, I think, a 4-line function. Sketch it out in some pseudocode. So we'll talk about that, and then we'll talk about how to insert into trees, and then we'll move towards deletion. All right, I will see you next time.